Welcome back. Let's do another example. On this example, I'm going to go ahead and give you this sort of template to organize your thoughts a little bit, to work through. But take a second, give this one a try, and I'll periodically kind of check in. Okay, hopefully you paused the video and gave it a try. This is probably going to be a process of getting a bit farther each time you try on your own. So, your 20-foot ladder leans against a wall. By the way, you're on the top. The base slides away at 2 feet per second. How fast are you falling when you are 10 feet above the ground? This is a classic example. There's a lot of neat things that happen if you look at this model really carefully. So the first thing you want to do is kind of just think through it. Do I think I can draw a picture in my head? Does it make sense to me? And then start to draw a picture. You don't have to go in this order. You don't have to do anything in particular. It's your model. But if you follow these steps, it'll probably be clear to whoever's reading, and it'll give you a little bit of direction. So I've got a ladder leaning against a wall. Right? Something like this. All right, and they tell me that my ladder is 20 feet, so this thing should be 20 feet. They also tell me that I'm on this ladder, or you're on this ladder. And I'm going to assume we're at the top. Not a very safe way to stand on a ladder, but you get the idea. So the base slides away. So away is this way. And if you got this picture in your head, you realize, oh yeah, that means the top of the ladder is going to go this way. And in particular, I'm going to go with it this way. Very dangerous, very scary. It's happened to me. I don't recommend it. Okay, so maybe you start to see this picture. Like, what is the shape happening here? And it looks like what we have is a right triangle. So identifying that shape is part of the game. Next, we probably want to start either labeling this or looking for my rates given. Let's go out of order. Let's look for my rates given, the ones we want. So the base slides away at 2 feet per second. That's definitely a rate. So let's call this dB dt equals 2. Well, if I'm going to call it dB dt, then I'd better label this thing over here b. Notice also that b is getting bigger, so that should be a positive 2 and not a negative. Sometimes people will make sign errors. But it also talks about how fast you're falling when you are 10 feet from the ground. So what we want is how fast I'm falling. Well, let's look at this picture for a second, and maybe let's label this picture some more. This other side of the triangle, I'm going to call it h. You could do a and b if you want to. It's your model, but I'm going to call it h for height. So how fast I'm falling is really how fast h is changing. So that is dh dt. So often I'll just draw the picture because I'm pretty good at these, but it is okay to kind of go back and forth between these different ideas to make sure everything is labeled well. And then there's one more piece of information, which is this when you are 10 feet above the ground. And I also would like to incorporate that into my model somehow. So I'm going to say this is just when h equals 10. And at this point, I'm pretty confident that I've gotten all the information up there into what I've written down here. Some people will start to label things like they'll label this arrow dHdt and the dBdt and they'll label this arrow dHdt. I find that creates a lot more problems than it's worth. I like to keep it clean, keep the rates of change over here and over here. I'll do my best to read what you write, but keeping it clean is definitely a skill worth achieving. So let's go ahead and write down our variables, help out our reader, help out ourselves. So it looks like we have a b, which is our base. We have an h, which is our height. And in a lot of these we'll have a t. In this case we definitely do, which is time. If something is actually moving, then you probably have a t equals time. But you don't have to. Not everything has to do with something moving. Okay. What we need now is some relationship between, well, base and height. Right? That will eventually give us a relationship between this rate and this rate. If only I had some kind of a relationship between the base of a triangle and the height of a triangle when it's a right triangle. If only I could connect the lengths of the sides of a right triangle somehow with some sort of a theorem. Oh yeah, the Pythagorean theorem. So a squared plus b squared is c squared, or in this case, b squared plus h squared equals 20 squared. Notice for a second that 20 is not changing. So I feel very confident labeling that ladder as 20, knowing that's not changing. If it was changing, I really wouldn't want to plug in that 20 yet. Okay, next up, we want a relationship between their rates of change. So if you got this far on your own, you did amazing for your second example. If you didn't, maybe take a second and make sure this really, really makes sense to you, because I guarantee you there are more triangle problems in your future. But now, see if you can do this last step, right? We've done all the geometry that's going to happen. Now it's just implicit differentiation and plugging in. So see if you can get this part done on your own. I'm going to go ahead and do it, though. So this, if I differentiate with respect to t, looks like I get a 2b, but b is a function of t, so the way I do my chain rule, db dt. Same with h. H is also a function of t, so the 2 comes down, but my chain rule says take out that dh dt, multiply by it. And then I need the derivative of 20 squared. That's 400. Doesn't really matter. What is the derivative of a constant? Oh yeah, that's 0. Nice. Some people will write b prime and h prime. I don't. I really like to emphasize that what you're doing right now is multivariate calculus. There's no reason why we couldn't make a model with many, many variables, with 100 variables, and you could do the same thing. A little bit of notation would be helpful for that. But in many ways, you are practicing not just modeling, but you're practicing modeling, in this case with 3 variables, but sometimes with 4 or 5. So congratulations. You're doing great. Okay, now that we've taken our derivative, we are allowed to plug in these other fun facts, like dB dt is 2 and h is 10. Once I plug those in, I really have fixed it to a particular kind of point in time. And so things stop moving. Let's do that. So 2b times dB dt is 2 feet per second, plus 2, we care about this when h is 10, times dh dt, which is how fast I am falling. Okay. I can't quite solve for dh dt yet. I still have this b. So this will happen sometimes, and it means that secretly you probably do know what b is at this moment in time. Maybe you already thought of this, but I have this beautiful right triangle with a 20 here, and when h is 10, the question is, what is b? Oh yeah, we could go back and solve for that, because 10 squared plus b squared equals 20 squared. The hypotenuse is always the one by itself. So let's solve for b real quick. It looks like b squared is equal to 400 minus 3. That's a terrible 3. 300, which is equal to, I don't know why I did 300. I got ahead of myself. 400 minus 100, 20 squared minus 10 squared, which is 300. There we go. So b is equal to the square root of 300. Notice the math says plus or minus square root of 300, but I know that b is a length, so I know I want the positive one. Fantastic. Almost there. Let's plug that in to our equation. So it looks like I'm going to get 4 times the square root of 300 plus 20 dh dt equals 0. If I solve for dh dt, I'm going to get, I'm going to get this negative 4 times 300, root 300, and then I'm going to need to divide by 20. So I did that in one step. I could go another here and say this is the negative square root of 300 over 5, canceling that 4. Heck, I could even, if I really want to go to the limits, I could bring that 5 into my square root as a 25. And so this would be the square root of 12. 300 over 25 is, if our math is right, 12. I could even go further if I really want to. I'm just addicted now. 12 is 4 times 3, so this is, I bring that 4 out as a 2 root 3, if you want to go all the way. Whew, okay. You don't always need to, but definitely make sure you could if you wanted to. Otherwise, you're just cheating yourself. Here we go. Great answer. What this is telling me in words is that, oh yeah, at that time, I'm falling at 2 root 3 feet per second, which is actually quite fast. Now you ask, Austin, what about the negative? Well, let's think about this for a second up here in my model. H is getting smaller. That's why it's a negative. We expect a negative because it's getting smaller. But when I say how fast am I falling, we kind of assume we mean in the downward direction. So, if H is decreasing at if H's rate of increase is negative 10 feet per second, then I'd be falling at positive 10 feet per second. So, in English, that's what's going on. Very cool. Very cool. It's oddly empowering. I do want to just jump back here for a quick second when we look at this and say, well, what happens as I get close to 0? Just as a curiosity, what happens as H gets really close to 0? And what you'd see is that as H gets really close to 0, B blows up. B goes off to infinity. And so dH dt also ends up going off to infinity. In fact, we could, if we were just bored or curious, we could solve for dH dt here and say, well, that is going to be 2b times dB dt over 2h times dH dt. I lost a minus sign there. Those 2's also cancel. Okay. Oh, sorry. I don't need that dH dt. It's just an dH dt is what I'm solving for. And what you see is that as that H gets small, this B gets big. So the bottom gets small, the top gets big. This is fixed at a 2. And so the rate I'm falling is actually going off to infinity. So there is something wrong with this model on the edges. This often happens with models, is that on the far edges, it becomes unrealistic. It's worth thinking about how that works and why that works. So just a neat fact to think about, the deeper thoughts of analyzing models afterwards. That was not asked of you for this particular problem, but if it's neat, maybe it's worth saying out loud. Okay, I'll catch you at our next example.